First, I would like to thank the organizers for inviting me. It's my great honor to be here to present my work on two-way fixed effect. And this is a joint work with my amazing collaborators, Dimitri, Hito, and Sharma. So for this audience, I think two-way fixed effect should be familiar to most of the people here. But just to make sure that we are all on the same page, the two-way fixed effect model assumes that the outcome for unit I and time t can be decomposed into several terms. And in particular, the important ones are the unit fixed effect, which is time invariant, and time fixed effect, which is unit invariant. And also there's a treatment effect term, which assumes that we have a homogeneous treatment effect. So motivated by this specification, we can define the two-way fixed effect estimator by just running the regression. And in particular, we can regress the outcome on the unit time dummies and the treatment assignment together with some exogenous covariates. So turns out when you only have two time periods, and if all units only get treated in the second period, then this is identical to the definitive estimator. And moreover, under this model, if this model is correctly specified, we know that this estimator is going to be unbiased. But people are not satisfied with this. And in recent years, there has been an explosion of DID and two-way fixed effects literature, showing that if some of the assumptions here are violated, say if you have heterogeneous treatment effect, or if you have violation of parallel trend, then this estimator is going to be biased. And motivated by this concern, a lot of alternative methods have been proposed. And here, there's no way to exhaust this literature because it's so huge. And I just list a few. And the central question for us is that, has the two-way fixed effect been fully understood? And of course, the answer is no. Otherwise, I wouldn't have been here to present. And here's a summary of our contributions. So first of all, we introduced a class of estimate called W average treatment effect, or DATA in short. So I would like to emphasize that estimates are quite important. In the literature, people have proposed so many methods, but for most of them, they are estimating different estimates. So strictly speaking, the methods are not strictly comparable. And here, I think it's okay because different settings have different things that are important, but I think we should make this super clear. And then for this class of estimates, we propose a class of estimators called reshaped IPW estimator. And I think most people should be familiar with IPW part, but here our innovation is really in the reshape part. And turns out we show that this class of estimators permits valid design-based inference. And in particular, in this setting, we consider a finite population framework where the effect can be varying arbitrarily with time and unit. And also the inference can be valid for many dependent designs. So it's not just for ID samples. It can hold for sampling without replacement, two-stage randomization, and so on. And then more generally, we show this doubly robust result, which is that our estimator will converge to our estimate if either the treatment assignment model is known or well estimated, or the two-way model is correct. So it's very similar in spirit to the double robustness in the cross-sectional literature. And I know a lot of people get confused here because it seems like double robustness is a model-based concept. And here we also talk about design-based inference. So in this talk, I don't have time to dig into this. But roughly speaking, our double robustness result is a strict generalization of design-based inference. Because in some sense, you can easily unify design and model-based inference using a more general framework. But again, that's a very technical point, which I will not delve into. And one point we want to make at this stage is that all these results and estimators are not restricted to staggered adoption. And we want to handle general designs where the units can get into and out of the treatment at any time. So the first part of the talk will be defining the estimand, the estimator, and briefly talk about the design-based inference. So just to introduce the notation here and setting here, suppose we have a balanced panel with n units and capital T time period. And throughout the talk, I will focus on the setting with a fixed T. So it turns out, although like the fixed T setting sounds simpler, but turns out this is harder than large T, especially when you have unmeasured confounders. And roughly speaking, this is because that when you have unit fixed effect, then in this setting, they cannot be consistently estimated because for each unit fixed effect, you only have capital T samples that carry the information of it. But if capital T is fixed, then you don't have asymptotically infinite samples. And we, excuse. So we will also consider a binary treatment. And we use Wi little t to denote the treatment for unit I and at time t. And then we use this bold-face Wi to denote the treatment path. And in the first part, because we're going to talk about design-based inference, so we'll use the propensity score. And in particular, because this is a treatment path, so we will use the generalized propensity score, which we call pi I, that is defined as the distribution of the entire treatment path. So at first glance, it may appear to be a complicated object because in principle, you could have 2 to the capital T possible values. And this doesn't seem to be something that can be estimated except in an experiment. But in many cases, we don't have all 2 to the T possible values. So for example, if you have a staggered adoption, then you can have at most capital T plus 1 possible assignment, which are always always treated and also treated at each point. So from that perspective, this generalized propensity score is not as complicated as enumerating all 2 to the T possible values. And then we will consider potential outcomes, which are defined as YIT1 and YIT0. And in this talk, we will assume SUTVA, meaning that the observed outcome equal to YIT1 if it is getting treated, or YIT0 if it is in a control arm. And for this part, we will assume that the potential outcomes are fixed with essentially no restriction on the magnitude of this potential outcomes. So given this setting, now we can define the unit time specific effect as the difference between YIT1 and YIT0, and let's call it tau IT. And again, we want this tau IT to vary with time and unit arbitrarily. And then we can define the date in the following way. So first, we take an unweighted average over units for each time period. And this will give us a time-specific AT. And then we will weight this time-specific ATE by some user-specified weights. So one special case would be the equally weighted date, that is to weight each time period equally. So essentially, in this case, this is just the unweighted average of all tau IT for all units and times. So this estimate has been studied in the literature before. Okay, in order to estimate this estimate, the first thought would be to use IPW estimator, because here we assume the knowledge of the propensity score, or at least we assume that we can estimate the propensity score. So for cross-sectional data, the celebrity IPW estimator has several versions. And here I want to talk about one version called Hayek IPW estimator, which is defined in this way, where it's the contrast between these two terms, and each term estimates the treatment arm specific mean outcomes. So the usual textbook version of IPW estimator use the number of units to normalize these two terms. But here, this version of IPW estimators using the sum of inverse propensity score. So compared to the usual version of IPW estimators, this estimator is shift invariant, and also you don't need to estimate the propensity score exactly correctly. You can allow for a multiplicative misspecification. But anyway, so the reason I bring up this version of IPW estimator is that it has another formulation, which is a weighted least square estimator. So it turns out it is equivalently formulated as the following estimator, where here you have the least square objective that includes an intercept and the treatment assignment, And then instead of running this least squares, you reweight it by the propensity score. And you can show that these two things are equivalent. So this gives us an idea that we can probably reweight the objective function using the treatment assignment mechanism. So we know that in causal inference, weighting is a very, very powerful technique. But when people talk about weighting, they usually talk about weighting the samples. And here, this is another type of weighting, which is to weight the objective function. In principle, weighting the objective function will induce a weight on the samples. But here, this is just another perspective to weight different things. So motivated by this equivalence, we can think about the generalization to the panel data, where here we can replace the least square objective by the two-way fixed effect least square objective. And here we can include both the unit and time fixed effect. And then we can reweight it by the generalized propensity score. But the question is, what does this converge to? So maybe now I can take a quick pause to see if there's any question on the setting, just to make sure that there's nothing confusing here.
No questions so far.
Great. Thanks. Okay, I'm going to move on. So now the next question I'm going to address is the asymptotic limit of this estimator. So let me give you two examples, both with 3 time periods, just to illustrate whether things are standard or non-standard. So the first example is what I call transient treatment, where each unit will get treated at exactly 1 period, or they will never get treated. So it turns out, in this case, the IPW estimators would converge to the equally weighted date. So this seems to be very intuitive, right? Because here, if we weight everybody using the inverse generalized propensity score, we should expect to get something symmetric. So far, so good. But then let's turn to another example, which is staggered rollout. So in this case, as long as the unit get into the treatment, it will never leave. So here, the support of the treatment path will change. And turns out, in this case, the limit of the IPW estimator is no longer equally weighted date, but rather another date with weight 0.3, 0.4, and 0.3. So it doesn't look so bad, but I think to me, when I first saw this, I feel puzzled because why do we get these numbers? Why do we put more weights into the middle? And then you can slightly generalize this to capital T time period. And turns out for transient treatment, you still get equally weighted date. But for staggered rollout, you got something like this, where you will still get non-negative weights for each time period, but this set of weights will put the most mass into the middle. So let's say if you have 30 time period, then you will put most of the mass on time 15 and 16, while putting little mass on time 1 and time 30. Well, you may say it's okay because all the weights are non-negative, but on the other hand, I would say these weights are not very interpretable. So the question is, suppose we want data with pre-specified weights, then how can we achieve that? So one reason to think about potential outcome is that you can define the estimate prior to your data. And here is the same logic that we want to define our estimate before looking at the data. And one way to do that is to pre-specify weight and then think about how to get it. So here we propose a class of estimators called reshaped IPW estimators, which is a very simple modification of the IPW estimator, except that instead of weighting everything by 1 over the propensity score, we weighted by some number divided by the propensity score. And this number could depend on the realization of the treatment path, but it will not depend on the unit or time. So we will summarize this object into a capital Pi, which after renormalization, we can treat it as a data-independent distribution on the support of the treatment path. Because here, we should notice that if we rescale this weight by a multiplicative constant, this estimator wouldn't change. So that's why we can assume without loss of generality that this capital Pi is the distribution. So turns out the IPW estimator is the special case with the uniform distribution over the support. And also, another view of this is that if we have a completely randomized experiment where all generalized propensity scores are equal, then this estimator will reduce to the standard two-way fixed effect estimators if we take this capital Pi to be the same as the randomization scheme. So this makes this estimator connected to both the IPW estimator and the standard two-way fixed effect estimators. So now the question becomes, for what capital Pi does the estimator converge to a date estimate with a user-specified weight Kc? And here is our main result. So we show that given any support and capital Pi with the same support, then our IPW estimator converges to the date with weight Kc if and quote unquote only if we have this equation, which is very complicated and you don't need to read it. And turns out this is just a set of quadratic equations that only depends on the support, meaning that you only need to tell me what possible assignment path that you could have. You don't need to give me any data in order to decide how to choose this Pi. So that's why we call this a design equation. And also, it is a set of quadratic equations on these unknowns defined by capital Pi. And because capital Pi is a distribution, so you can view the density at each point as an unknown. And this data equation will be a set of equations on those. And of course, you need some constraints like positivity and simplex. So in principle, we know that in general, we don't know whether a set of quadratic equations have solutions or have infinite solutions. But fortunately, for many practical cases on the support, say DID, crossover, stagger rollout, transient, we can find the closed form solutions. And if we don't have these designs, then you can still use a generic solver based on nonlinear programming to at least find one solution if it exists. And here's the results for our stylistic example. So again, for transient treatment, we can show that these four numbers, or the solution of the data equation, can be written as a convex combination of two vectors. The first one will put all the math onto the always control units, or never treated units. And the second is putting equal mass onto ever treated units and zero mass on the never treated units. And of course, we don't want anything to be zero, so we will take a convex combination. So one consequence of this is that the uniform distribution is one solution if you take lambda to be 1/4. So this confirms that the IPW estimator works in this case, because we know that IPW estimator corresponds to this our IPW estimator with the uniform distribution as the capital Pi. But for stagger rollout, the solution will be different. And turns out it will be the convex combination of these two cryptic vectors, where the first one is 2/9, 3/9, 0, and 4/9. And the second is the reverse of this. And we essentially show that for any convex combination of these two vectors, we will have a consistent estimate for the equally weighted date. And in particular, the uniform distribution is not a solution. And that's kind of corroborates with our finding before, because we show that the IPW estimator is converging to another date than the equally weighted date. So this shows some non-standard things coming out of this data equation. So I think now it's time to take another pause to see if there's any question.
So I guess I have a question here. So in general, you seem to have many solutions to this quadratic equation. So I suppose you could choose any among them. So the natural way would be to choose the one that's the most efficient, I suppose.
Yeah.
Can you say a bit more about how to choose?
Yeah, that's a great question. So here, first of all, we found, at least in all these cases, the solution sets often has a very simple structure. So for example, it's going to be a one-dimensional subspace. And so we can parameterize these distributions using this single parameter. And then, as you said, we have the flexibility. So we can try to find one that maximizes the efficiency. So one way to do it is to estimate the variance of the estimator and choose the one that minimizes the variance. So in our case with fixed t, you can show that asymptotically it's a valid choice. But in practice, in order to avoid overfitting, you can do some data splitting. So we haven't explored this in our paper because there's another interesting aspect, which we think is more appealing. And that is to address the lack of overlap. So say if you have a randomized experiment or observational study with staggered adoption, but somehow there are very few units that are assigned at period 2, meaning that you have a fair share of units with this, and always treated. But there are very few units with 0, 1, 1. So in this case, we know that we don't want to overweight those units. So if we estimate the propensity score, those propensity scores tend to be small. So in this case, we can try to pick our lambda close to 1, so that for those units, this reshape factor is close to 0. And then it will somehow cancel out some of the effect from those small propensity score. So for 3 time period, you can easily see how things will be changed. But for general capital T, it's still not clear how to address this generically. But I think being able to address the lack of overlap is very important in panel data because we have too many possible assignment paths. And it's very rare to have a case where every possible path has large propensity score. Okay.
And, I think David had a question as well.
Okay, so I have 2, and the first is totally optional. You seem to be like, yeah, don't look at the date, you know, like sort of like is there if it appears opaque to us, like is there some degree to which like you can explain like why it is what it is and why the solutions look like what they look like? If that's not the right question for now, feel free to just pass on that.
No, that's a great question. So here, essentially, data equation tells you what this should be. By the way, I think before addressing that, I would like to say that it is only this part that is independent of data. So the other part are still data dependent, just like the cross-sectional case. But in cross-sectional case, you don't have many options because here we can show that no matter how you choose this, it will be the same. So essentially, you can think about IPW estimator without loss of generality. But in the panel case, because you have more than 2 possible assignments, so now you will have the flexibility here. And it's just this part that is independent of data. And then this data equation just gives you how we should choose it. But if you want to get more insight on the solution set of this equation, I'm not sure if that's your question.
Yeah, that's kind of, or if it's not the solution set, like why is the equation what it is? Like I feel like I can kind of see like time differencing in there and some stuff, but it has, yeah, I don't entirely understand it at this point. I'm wondering if there's a
right. So my best answer at this moment would be that this is just an algebraic result. We don't have a better answer to this question than what it is.
Okay.
Yeah. And one thing that worth mentioning is that the reason we have something non-standard here is because of this unit fix effect, which can be treated as incidental parameters. And in the fixed T setting, we can show that this so in the fixed T setting, we have n times T samples in total, but the number of incidental parameters is n, which is proportional to n times D. So in this case, this will create some irregularity of the solution path. So, sorry, the solution set, so to speak. So the only thing I can provide is that the incidental parameters make the structure more complicated, but I couldn't give any more intuition on why we end up with something like this.
Totally. All right. Is it a good time for me to ask one more, or should I?
Yeah, go ahead.
All right. So you said it's not necessarily satisfiable, correct?
Right.
So have you observed it to be not satisfiable in any instances?
Yeah.
And then so like to what degree does an approximate solution help? Yeah, I guess it's kind of.
Yeah. So first, I'm going to address one of your points in the next few slides. And
Okay.
but just a quick answer to your question. So there are cases where you don't have a solution, but that's the case where, so strictly speaking, that means if you just give me a random cassette,
Okay. Yeah.
then the solution may not exist. But another view of the data equation is that you give me this capital pi, and I tell you what cassette it is. And we will give you one result in maybe 4 or 5 slides. Yeah. But in general, it will be very interesting to further investigate the mathematical structure of this equation to give a more qualitative description on when the solution exists. So far, we don't have that. We only show that for all these designs, the solution exists and we can characterize them. Yeah. Thanks for the questions. Okay, so if there's no more question, I'm going to move on. So for this set of estimators, we can first think about a case where we know the propensity score. So in this case, we can get valid inference. So it turns out for all of these designs, including Bernoulli designs or dependent designs like sampling without replacement, cluster-wise randomization, two-stage randomization, we can have a asymptotically conservative variance estimate, and hence a valid Watt confidence interval. So roughly speaking, we can find a valid inference for this estimator for any dependent designs that can be handled for cross-sectional data. So say if you have a bootstrap procedure that can work for these designs for cross-sectional data, then you can apply a similar stuff to our estimator in the panel case. So this is a very general result. And now to give you two other interpretations of data equation to just try to give you more sense of why this is and what this is. So the first thing is, as I mentioned before, if we have a completely randomized experiment where all capital pi I equals to pi, then this will reduce to the standard two-way fixed effect estimator. So then we show that the standard two-way fixed effect estimator will converge to a date. So that means the data equation gives all completely randomized experiment for which the standard two-way fixed effect estimator works, in the sense that it will converge to a user-specified date. So this seems to be a conflict with the literature that the two-way fixed effect estimator has negative weights, because this is one of the main criticism to the two-way fixed effect estimator. But turns out there's no conflict, there's no contradiction here, because we consider different sources of randomness. So in the literature, this assignment path are treated as fixed, but in our work, we treat it as random. So a high-level point I want to make here is that when we talk about weights, it's very important to specify the source of randomness, because that could affect the conclusion. So in the end of the talk, if time permits, I'm going to give you a more thorough discussion on this point. Okay, so that's one interpretation of the data equation, which is from the experiment perspective. And another view of the data equation is related to David's question. And that is, before, the way we frame this is to say, if we want to get a particular Kasi, then how should we set this capital pi? But another way to look at it is that you first give me the capital pi, and then I can give you the induced estimate or the effective estimate of this estimator, which can be defined in this way. And turns out we can show that for any capital pi and any time period, the weights are always non-negative. So you don't need any assumption on the support of the assignment path. You don't need any assumption on the capital pi. As long as it's a distribution, then we can show that you will get a date with non-negative weights. So those are the two views of data equation. So again, because this is so important, let me take another quick pause to see if there's anything confusing here.
Dalia, do you have a question?
Yeah, I'd love to ask a question. So kind of back to the discussion about if I choose, like that there may not be solutions for specific choices of psi. So here, if you at least choose simple ones, suppose equally weighted, I don't treat, like from a practical perspective, that could be enough, right? I mean, for a lot of applications, maybe they don't care to weight different time periods differently.
Right.
Would you be able to have solutions at least for that simple case, or at least a few of those like simple cases?
Yes, that's a great question. So here, what I show here is that for all of this, there are solutions. And
okay, so, but not, I thought for specific choices of psi, which is the weight for the time periods, right? If I understand that correctly.
Yeah.
Oh, so for any choice of the weighting?
Yeah, so for any of these designs, for any of this support, and if you choose Kasai to be the equal weight,
Okay.
You can find solutions. And in general, we can find pathological support for which the solution doesn't exist. But that's usually the pathological case where, for example, if not every period can be potentially treated, then there's no way to identify the ATE for that time period. So then as a result, it's impossible to identify equally weighted date. But for all of this, where you have the full coverage of all time periods, then you can find solutions.
Okay, great.
Okay, so if there's no more question, that will wrap up the first part. And then I will talk about the double robustness. So in order to talk about this, we need to introduce covariates. And here, in general, we could allow for time-varying covariate. But in any case, we will just compress everything into a vector, which will be denoted by boldface xi. And we just need this boldface xi to satisfy a latent ignorability assumption. But for now, to conceptualize it, you can just assume that this xi is strictly exogenous or satisfy the ignorability assumption. And here, our main point is not to say this estimator can address unmeasured confounders. It's to say how to use this actual information, how to use the ignorability assumption to make the estimator more flexible. And in our paper, we discuss cases with unmeasured confounders, but those are special cases which we need to take advantage of their special structure. But here, we're not going to dig into that. So with this covariate, we first use this covariate to fit an assignment model to estimate the generalized propensity score. So again, at first glance, it seemed to be an ambitious goal because you have 2 to the t possible assignment. But as I mentioned earlier, for many cases, you don't have the whole support. You only have a very small subset. So for staggered rollout, we know that the treatment assignment path will be reduced to the adoption time. So here, modeling the treatment path is equivalent to modeling the adoption time. And one view of that is to treat it as a time to event or survival time. So then we can use duration models to model the generalized propensity score. So for example, in one of our applications, we use the Cox proportional hazard model to model the staggered rollout. So this just to say it's not entirely impossible. And in many cases, like the policy evaluation setting, it makes sense to model the adoption time as a duration. And for general designs where the units can get into and out of the treatment, we can use discrete Markov model, conditional logic model, and many other models that can give you some sense of how things evolve. So here, a practical point is that with covariate, we can have a lot of ways to estimate propensity score. It's not like in the cross-sectional case, which is essentially estimating a We're also going to use this covariance to try to fit an outcome model. But here, the definition of the outcome model is trickier. So let's say, suppose you believe that your outcome model is a standard two-way fixed effect model, which can be decomposed as alpha I plus lambda t plus an interaction term, MIT. Then we only need to estimate this interaction term consistently. So for example, if we use the standard two-way model where this interaction term is a linear function of the covariance, then we just need to estimate this part consistently. So this is important because we don't want to estimate the fixed effect, because in our setting, we have a fixed t. So there's no way that we can get this fixed effect consistently. So that's why we don't want to say we want to estimate the entire two-way model consistently. So Michal, you seem to have a question?
Yeah, but you can keep going if you want to finish your point.
Oh, okay, yeah.
Asking.
Let me finish this slide and then take a pause. So then with all this set up, now we can define the more general version of our IPW estimator, which first modify the outcome by subtracting this estimate from the outcome, and then pretends the estimated propensity score to be the true propensity score. And then we run our IPWs on the modified outcome. That's the definition of the more general RIPW estimators in the cases with covariate. Okay, so let me pause here to take a question.
So I guess Andre Stracker was wondering whether, so you said the estimand as this unweighted average treatment effect, and then you try and find these pi that satisfy your equation.
Yeah.
You could do this more generally by specifying the estimand to be some weighted average, and then you would presumably have a different data equation.
Yes, exactly. So let me go back to it. Thanks for the question. So you see, the data equation depends on the weights. So here, this is a general result that holds for any weights. So if you have equally weighted data, then this will be 1 over t. But for general things, yeah, the data equation is indeed depending on the c.
Okay, I missed the c. Okay.
That's a great question. Thanks for bringing it up. Okay. So then once we have this estimator, we can show that this estimator is doubly robust in the sense that if either the assignment, it will be converging to the date if either the assignment model is well estimated or the two-way model is correct. So although our proof is very complicated, but the intuition is very simple. So first, if the assignment model is well estimated, that means the pi I hat would be close to pi I. And then this will reduce to the design-based inference approximately. And our previous results shows that this will give you a consistent estimate of date. So that's why we should expect that this estimator should also work. But on the other hand, if the propensity score is misspecified, but the two-way model is correct, then this is just a weighted least square estimate for the two-way fixed effect regression. And we know that the weighted least square, although it's not necessarily efficient, but it's always consistent as long as these weights behave normally, meaning that it's not too large or too small. So with some mild assumptions on the magnitude of this weight, we should also expect a consistent estimate of date, in which case, or under the two-way model, we know the date is simply the coefficient of the treatment assignment. So that's why we should expect our estimators to be doubly robust. And for many people who are familiar with this literature, you may want to ask, what is the difference between this notion of double robustness and the existing notion of double robustness in the literature, say Santana and Zhao for DID? Or you can, because the Kolesár Santana DID estimator is a combination of this estimator. So in general, you can also have a double robustness for CSDID. And turns out, these are two different notions of double robustness because first, we are based on fundamentally different assumptions. I don't know if I will have time to dig into that, but maybe if you're interested, I'm happy to talk offline. So because the difference between this the set of assumptions are complicated, but roughly speaking, they are very different. But also I want to address that our double robustness holds for non-staggered adoption. So if you have staggered adoption, then maybe you can say in practice, they're not so different. But when you have non-staggered adoption, I think this will be very different. Okay, so another point I want to make is about the version of double robustness. So people often say double robustness, but there are actually two versions of that, at least two versions of that in theory. One is what I call the weak double robustness, meaning that the estimator will be consistent if either model is well estimated. But there's a stronger notion of that, which says that on top of weak DR, we will achieve a smaller error if both models are well estimated. So here I will just give you a flavor of what this looks like. So let's say if we estimated these quantities from an external data set so that we can treat them as fixed, then this estimator will be consistent for the corresponding date if the product of two errors is small. And here, the delta pi roughly measures the accuracy of the treatment modeling or the propensity score modeling, and delta y measures the accuracy of the two-way model. So in the cross-sectional data, this is just the arrow to estimate the propensity score function, and this is the arrow to estimate the conditional expectation of the potential outcomes. And here we have an analogous version, which is slightly more technical. But the flavor is the same, is that the bias of the estimator or the validity of the estimator depends on the product of these two errors. And for inference, we just need the product of these two errors to be small or 1 over root n. And in general, we don't always have this external data set to give us independent estimate. So what we did instead is to use cross-fitting. So we can cross-fit pi I hat and mi hat, which are the propensity score and the outcome model. And as long as they are asymptotically deterministic, meaning that they will convert to something deterministic, then we can show that we can make valid inference, at least asymptotically. And this matches one of the weakest assumptions for cross-sectional data. And in this case, for doubly robust inference, meaning that we don't just want doubly robust consistency, we want the confidence intervals to work in a doubly robust way, then we will need independence across the units. So this is different from the design-based inference where we can allow for dependence. And that's because as long as you want to use cross-fitting, then you want the samples where you fit those estimates to be independent of the samples you apply those estimates. But one technical point is that this is not this equivalent to the standard cross-fitting, because here we only cross-fit the nuisance parameter. But the whole RIPW estimator is still estimated from the entire sample. So that's why our argument is slightly more complicated than the standard cross-fitting. So that wraps up the second part. Let me take another pause to see if there's anything confusing here.
Yeah, I think you can go ahead.
Okay, yeah. So next, I'm going to talk about one case study. So this is about evaluating the short-term effect of state of emergency in early COVID-19 pandemic. So it's been 2 years from the start of the pandemic, and you may still have a memory on the beginning of that because it was so dramatic. So on February 29th, 2020, the state of Washington first declared the state of emergency. And 1 month after that, basically all states in the United States declared the same thing. And after that, we started our virtual life. So here the goal is to evaluate the effect of state of emergency in the short-term economic activities. But we know that the high-frequency economic activities are very hard to get. But fortunately, we found an interesting data set released by OpenTable that gives us the daily data of year-over-year city diners, for example, restaurant in 36 states in the United States. And here's the snapshot of their app. But of course, this is not from 2020, because in 2020, you can expect that these numbers are all very negative. Because after the first day of state of emergency, the public will really get into panic. So they will try to get rid of going to restaurant in person. But at least we have this daily data, which can provide high frequency information. So here we will be interested in the ATE, or equally weighted ATE of the state of emergency on the dining rate during the first 14 days. And we all know that policy evaluation during COVID is complicated and it's challenging. And we have seen so many papers on that, but it's not easy to convince the audience that it's solid. But here, I want to say something special about this policy, because the state of emergency was kind of less confounded in the sense that it is almost the first policy affecting the vast majority of the public at the beginning or during the course of the pandemic. So compared to the mask mandate or vaccine, it is less confounded. And second, because we're investigating the short-term effect, the restaurant industry is responding to this policy effect or to policy very swiftly. So we should expect this to be immune to some long-term confounders. So I'm not saying this is a simple task. I'm just saying compared to many other policy evaluation tasks, this is relatively simpler. And another important feature of this problem is that there is an asymmetry in modeling the treatment assignment and modeling the outcome. Because here the treatment assignment is really the declaration time of state of emergency. And we know it basically depends on two things. One is the progress of the pandemic, and the other is the authorities' attitude. But on the other hand, the dining rate, at least in the short term, it's very hard to measure, or it's very hard to model because we know it depends on a lot of unmeasured behavioral variables. And it's almost impossible to collect those informations, at least during the first few days in the pandemic. So this kind of justifies why we want to use the assignment mechanism in our estimators. Because here, arguably, there's no outcome model that can be very convincing. But the modeling of declaration time is arguably easier. So here, just to demonstrate how we are going to use our estimators, we're going to include three covariates. One is the state level accumulated confirmed cases. The second is the vote share of the Democrats based on the 2016 presidential election data, which measures the attitude or proxy the authorities' attitude. And we also include the number of hospital beds per capita to proxy the amount of medical resource in each state. And here's a plot of the treatment status in days. So you can see this is a case of staggered adoption, and there are never treated units. There are always treated units, and most of the units will be in this range, and there's a fair amount of variation in the adoption time. So here, as mentioned before, we will treat the declaration of the state of emergency as an event, and we will fit a Cox model on that. So for those who are familiar with the Cox model, who are not familiar with the Cox model, it will just essentially model the CDF or the conditional CDF of this time to event. So once we have the CDF, we can take the difference to get a propensity score, because here the propensity score is essentially a density. So it's not very hard to get the propensity score from the Cox model. And then we can also do some diagnostics on the Cox model. And here's one, because one crucial assumption behind Cox model is the proportional hazard assumption. And there are some existing tests which can be used to assess how plausible this is. So here we test the proportional hazard assumption on each of the 3 covariates. And also we test it simultaneously. And at least we didn't find evidence against this assumption. But the caveat is that whenever you run a specification test, the failure to reject the specification doesn't mean you should accept it. So this is really a diagnostic. And our finding is that, so first of all, we'll use the Cox proportional hazard model to estimate the propensity score. And we will use the standard unweighted two-way model to do the regression adjustment to try to estimate the interaction term. And we show that our estimator is -4%, which is significant at 90% level. And as a benchmark, the unweighted two-way fixed effect estimator is way less than that and is not significant. So I don't want you to read into this result because, as I mentioned, this is really a demonstration and we only include 3 covariates. And if you really want to make this rigorous, you should try to collect a lot more other information. But this is just to show how we are going to use our estimate. So that's about case study. Maybe I will take another pause to take questions because the last part can be skipped. It's really just about discussion and extensions.
Hey, so I'll ask a question. So in this application, it may make sense to just run with the Cox model by itself and estimate the treatment effects that way, and not worry about two-way fixed effects at all.
Could you elaborate on that?
So I guess another approach in this application would just be take your assignment model seriously and only estimate it under the assignment model without doing the two-way fixed effect adjustment.
And then how are you going to include the Cox model?
So just use it to compute the propensity scores and then just use the standard IPW estimator.
You mean for each time period and then aggregate?
Yeah, something like that. So without adjusting for two-way fixed effects. So have you thought about that? Yeah,
that's a great question. So we can definitely do that. And in our paper, we have a whole appendix devoting to this issue on how should we compare our estimator with different versions of other IPW estimators. So first of all, I would like to say that we don't want to say that design-based inference is something we should do. We really just want to make the two-way fixed effect regression more robust. So instead of calling it double robust, I recently talked with my co-authors and we somehow want to change it to more robust. Because the point here is that everybody is running two-way fixed effect regression, or at least two-way fixed effect regression is a very good starting point. So now the question is how to make it more robust by including this actual source of information. So I think including the fixed effect could be useful there. But another motivation to include the fixed effect in the regression adjustment is that we know that this time invariant unmeasured confounder will play an important role in this type of settings. So if we can take them off, or then at least in some settings, we can make our estimator more efficient, because essentially this will take out a fair share of variability from the outcome. But of course, if you truly believe your design model, then you can still just use that without doing any regression adjustment. So this will be the same story as in the cross-sectional case, where let's say if you have randomized experiment, should you still use regression adjustment? I think the current consensus is that you should probably still use that because that will give you some free lunch, at least asymptotically. Yeah, but I think for this application, we should also report that result. I think that's a very good idea. Okay, So in the last 4 minutes, I want to give you some interesting discussions around this estimator and also on some general issue. So the first one I want to discuss is the negative weight. So as I mentioned before, the literature says the two-way fixed effect estimator is not good because it doesn't converge to a convex combination of individual treatment effect for most designs. But our work shows that the two-way estimator does converge to date for any design. And as long as the data equation has a solution, it can converge to a pre-specified date. Or in general, if you just give me a capital pi, then at least I can show that it will converge to something with non-negative weight. So is this a contradiction? No, that's because we consider different sources of randomness. So I want to illustrate on this point. So the weights discussed in the literature shows that conditioning on the assignment, the two-way fixed effect estimators can be decomposed in this way, where for each tau it, there's a weight that depends on the treatment assignment. So the result proof in the literature shows that for most designs, there exists at least one weight that is negative, almost surely. But here, what we show is that because we also take the assignment as random, so our limit will be the expected version of this, roughly speaking. And we show that for any I and t, the expected weight is going to be positive. So these two results are not contradicting. And this is an illustration on one simulated data. And again, the simulation detail are not important. So in the left plot, I give you 3 realizations of the conditional weight. And you can see for each of them, there is a fair share of weights that are negative. So this is the same as what the literature found. But then if you take the expectation, the unconditional weights could all be positive. And this is just for the standard unweighted two-way fixed effect regression. So this is not always true, because you can imagine if there's no much randomness in the assignment, then this plot will be close to this plot. Because in that case, the random assignment is close to the deterministic assignment. But there are cases where even for the standard unweighted two-way fixed effect regression, the estimator can still put all non-negative weights for all units and all times. So this is because for these realizations, the places where the negative weights are put are different across different realizations. So after aggregation, all of them can be non-negative. So that's a point I want to make, because when talking about weight, we should really specify the source of randomness. We can't say this estimator is bad because it has negative weights. We should say under what model, under what sources of randomness do you think it has negative weights? And different source of randomness can give you different answers to that question, to that same question. So that's the first point. And the next point is about how to handle dynamics. So in the previous sessions, we focused on the case that is static, in the sense that we only define the potential outcomes as a function of the contemporaneous treatment. And this implicitly excludes the dynamics or the temporal spillovers. But here, as I mentioned before, this objective weighting is a general principle. And in the cross-sectional case, we use the inverse propensity score to reweight the least square objective. And in our talk, we reweight the two-way fixed effect least square objective. But in general, you can also reweight the event study. So for example, here you can include the lag and the lead. And the question is, what does this converge to? So this is something new that comes out of our revision. And in this case, it's natural to consider short-range dynamics where the potential outcomes can depend on the contemporaneous treatment together with the past and future treatment. So this is setting that considered in a recent paper by Bochnov et al. And I think this setting is understudied. So for staggered adoption, we know that we can reduce all the potential outcomes into the adoption time. But for general settings, we don't have that. So then if you consider all past treatments, the number of potential outcomes is going to be exponentially large. So we will run into the curse of dimensionality or the curse of large time period. So in that setting, I think it makes a lot of sense to think about this short range dynamics, because in many cases, it's general enough. Because we don't expect something happened 10 years ago to have a huge effect on today. And in this case, the results become much more complicated, but we can still handle some of those. So here, this is a simple example with 3 time periods, and we only include 1 lag time period. And then for transient design, if we only restrict ourselves into IPW estimators, we can show the limits of those 2 estimators. So in order to show the limit, we first define this tau t01 as the effect of the contemporaneous effect. And we can also define tau t10 as the effect of the past or 1 lag effect. Then we can show this peculiar result that this 2 estimator will converge to some weighted average of these quantities. And again, these weights are data independent. They can be computed from something like the data equation. But one interesting thing is, if we don't have time heterogeneity, then these 2 estimators will converge to the right thing that we should expect, in the sense that the tau 0 hat would converge to the contemporaneous effect, and this is typo, tau -1 hat will converge to the effect of the lag 1 outcome, lag 1 treatment. And for staggered adoption, the numbers completely changes. But again, if there's no time heterogeneity, then we still have the similar result. So this is just to say, this is just a very quick peek at a host of new results. But this is just to say that with this more general technique on objective weighting, we can handle very complicated dynamics. And in general, as long as you have your own specification, you can always imagine that you can add this inverse propensity score or reweighted IPW weights onto your regression. And maybe you can get something interesting there. So just to wrap up, in this talk, we studied IPW estimator and showed that it converged to a date with non-negative weights, but the weights are not quite interpretable. So motivated by this concern, we proposed the reshaped IPW estimator that solved this problem. So it permits valid design-based inference for most practical designs. And also it is doubly robust and work for general designs, not limited to staggered adoption. And in practice, this empowers the users to leverage the information from the assignment model, as I demonstrated in our COVID example, because there we have a lot of knowledge in the assignment model. So we should use it. And here we give one way to use that in a principled way. And moreover, from an implementation perspective, this is very easy to compute, as long as you have a software that supports weighted least squares. And finally, the objective reweighting is a very powerful general strategy that can be used in many other settings. For example, you can consider event study. You can consider more general panel data models. And it will be open question on what that will give you, but I think that will be a good starting point to try. So with that, I would like to thank you all for your attention.
Thank you so much, Lihua. So now if there's any questions in the audience, we can open the floor.